All right, today's lesson is on modeling with quadratic functions. We're going to use what we know about graphing and solving quadratic equations to find some things about real-world quadratic equations. So in our first example, we're starting with the height in meters of a ball that's hit vertically upward, and we're modeling that based on time, seconds after it is hit. And we have a quadratic equation that represents the height of that particular ball. This quadratic equation we should recognize is in factored form. And because it's in factored form, that means we can find our x-intercepts by inspecting the two factors. That's important because the first question we're answering is how long does it take for the ball to reach its maximum height? Whenever we read maximum or minimum, that means we are looking for the vertex. So let's think about those two x-intercepts. Our first factor is 2t. So our first intercept is at 0, 0. Our second factor, is 18 minus t, and that would give us an x-intercept of 18. So remembering that each quadratic is perfectly symmetrical, the x value, in this case our t value, of the vertex would be the exact middle of these two x-intercepts. We can add them together and divide by 2, and that would give us 9. So it takes 9 seconds for this projectile to reach its maximum height. The second part of the vertex, the y or h coordinate in our case, would be the maximum height of the ball. Once we know that x value, we simply plug it back into our quadratic equation. You can plug it right there into its factored form. Every t was replaced with 9 seconds. And this will tell us the height at 9 seconds, which will be its maximum height. We get 2 times 9 times 9, which is 2 times 81, which is 162. So that would be 162 meters as the maximum height of the ball. So 162 is our vertex. The last question asks, how long does it take for the ball to hit the ground? So there are no numbers there, but we need to understand that when it hits the ground, height is 0. So we are setting our whole equation equal to 0. This is requiring us to solve for an x value, in this case a t value. Now, since it's already in factored form, we've already seen that when we found the x-intercepts, which are the same as the solutions, that we have time equals 0 and time equals 18. So if time equals 0, this is the exact moment that the ball was thrown, and this is when it lands. So 18 seconds is how long it would take to hit the ground. In example number 2, we have the model that represents the cost of making a certain number of skateboards per day. So the cost depends on how many skateboards we make. We should look at this quadratic and know that it is in standard form. The only piece of the graph we can see from standard form is our y-intercept, which would be 0 and 244. So going forward, we'll see if that is useful to us. The first question asks us how many skateboards would be made per day to minimize the cost of production. This is a quadratic that opens up, so when they refer to the minimum, this is another question that's asking about the vertex. Since we are in standard form, we need to remember that the vertex is x equals the opposite of b over 2a. In our equation, a is 1, b is negative 24, and c is 244. The opposite of b would be positive 24, and we're going to put that over 2 times 1, which would be 12 skateboards. If we make less than that or more than that, our costs go up. Now that we know how many skateboards to make, what are the actual costs, we need to plug that x value back in to find the y coordinate of the vertex, which would be our cost. You can plug that into a calculator, into Desmos. When you simplify, we get 100, and that would be in dollars. So if we make 12 skateboards, our costs are $100, and that's as low as they can go. That's the minimum. If no skateboards are made in a day, so we know we've already found the vertex, we're not looking for that. We're not asking when the cost is 0. That may not even be possible. We're asking what happens if x is 0. We'd still have to pay rent. We'd probably still have to pay our employees. So we are looking to evaluate in this case. We have a particular value of x that we're curious about. So we're going to plug 0 in to our cost function. And you might recognize this number. It is 244, which was our y-intercept. So that tells us when 0 skateboards are made, our costs are $244. In our last example, the driver of a car that is traveling downhill on a road applies his brakes, and we have a quadratic model that represents the speed of the car. As we look at this form, we should recognize that it is in standard form. It has a negative a value, so it's a quadratic that opens down. So when he applies the brakes, since the car is traveling downhill, it still accelerates a little bit before it begins to slow down again. So our first question is, how fast was the car traveling when the driver applied the brakes? Well, he applies the brake at the second that this model begins. So that is asking the original speed when time is 0. So we're going to plug 0 in for our t value, our x spot, and you should recognize, hopefully, that that is the y-intercept, which we can see by looking in standard form, which would give us 80. So it would be 80 kilometers per hour when he initially applies the brake when time is 0. Our second question asks us to find maximum speed. When we read maximum, again, we should think about the vertex. Now, our vertex in standard form can be calculated by doing the opposite of b over 2a. In our equation, a was equal to -4, b was 12, and c was 80, just as a reminder. So the opposite of b would be -12 over 2 times -4, which is 1.5. Now our x value is in seconds. That's actually the time it takes to reach the maximum speed. So he is accelerating. That's when the brakes finally catch. So in order to find that maximum speed, we have to substitute 1.5 back into the equation because speed is like our y coordinate. So we have to find the x first. So replace all of your t's with 1.5, and you can certainly use a calculator for this bit. When we plug in 1.5 and simplify with our calculators, we get a speed of 89 kilometers per hour. When we ask how long it takes the car to stop, we are asking when is the speed 0. So we are setting the whole equation equal to 0, which means we are solving the equation. So I'm always going to try to solve by factoring first, and I want to make my life easier, so I would divide both sides by -4. I know that all of these terms on the right are divisible by 4, so we get t squared minus 3t minus 20. And if I think, can I factor that? I would be looking for factors of -20 that add to -3. I've got 1 and 20. There's no way that works. 2 and 10, 4 and 5. And I'm out of factors of 20. So since we can't factor this, we're going to use the quadratic formula, where a is 1, b is -3, and c is -20. Now, you could also use the quadratic formula with the coefficients that were in the original equation, which were -4, +12, and +80, and you would get the same result. So that's not going to matter as we simplify. When we fill in our quadratic formula, I'm going to use my simplified version. The opposite of b is 3, plus or minus the square root of b squared minus 4 times a times c all over 2a. As I go through and simplify my radical, 9 plus 80 would give me 89. And because we're talking about the real world where we wouldn't express speed as a radical, 3 plus or minus the square root of 89 over 2, I'm going to break this out into the two solutions, use a calculator to simplify, and get my answer for how long it took this car to stop. So we have 3 plus that root over 2. And again, go to your calculator, plug that in. That simplifies to 6.22, which would be seconds. And 3 minus the square root of 89 divided by 2 would give us -3.2 seconds. Now, obviously, we can't go back in time. This is what we would call an unreasonable answer in the context of the problem. So we want to eliminate that. We don't want to tell anyone that we went back in time to stop our car. The only good answer in this context, in this problem, is 6.22 seconds to stop the car.